All right.
All right, good evening, Guy-Vincent.
Good evening, Marcel. So, how are you?
I'm quite good.
Excellent, excellent. All right. So today we want to do two things. We want to review quickly the first assignment, go over some of the mistakes that we have seen, and show you a solution very quickly. And then we are going to talk about the new assignment, assignment two,
Yep.
which was or will be posted later today or tomorrow.
Yeah. So for assignment 2, we'll show you the interface, how it's supposed to look. We'll explain the game, and then we'll talk about an important concept called the MVC Model View Controller.
Exactly.
All right, first part.
So yes, for the first assignment, we saw that some of you had issues, and the kind of errors we got were, often along the same line. And so Marcel just created some nice examples of codes that would show some of the problems that you guys had, some of you had, in the initialization part where you were supposed to supply the data to the objects, as well as some of the computation that was done to compute maybe the costs or the average.
Yes, and really one of the intent with those examples was to convince you that these were things that were not as complicated as you thought, that they were
Absolutely.
much more simpler than you thought. But because you were trying to solve everything at once, it made things more complicated. So my example breaks things into chunks that are more manageable.
That's right.
All right, so you'll see we'll post something on the web, on GitHub. It's going to be called something like samples, has several subfolders, each presenting different challenges. I'm inviting you to try to find the bugs. So in each of the folders, you find a README file. It says how many bugs there are, and you should try to find the bugs and
try to find more bugs.
More, yeah. If you can find more bugs, that would be great. And then you can discuss what you found on Piazza.
Yes, that would be a perfect location to discuss, especially if you find more bugs.
Yes. Okay, so maybe we can turn to the description.
Yes, so that was the assignment. So I'm just going to jump right to. So the first question was, okay, you had some introduction here and some explanation as to why you were to compute that, but at the end of the day, that's what you had to compute to update theta 0 and theta 1 iteratively following that formula.
Correct.
And everything else, well, is just an explanation as to why you have to do that. So if we look at the code that is required for that, so here's my linear regression class, and so you were provided all of that. So when you create it, you are going to say how many samples you're expecting in this instance. And so, well, this is stored in this variable here. So we were using here a small trick here, because we are going to store the samples and their corresponding values in an array. And so we have to predefine the size of the array. And but initially we have an array that is big enough, large enough to hold all these samples, but we haven't received any sample yet.
That's it. So when we say new linear regression object and we pass the value 1000, what we're saying is you're a linear regression object that should be ready to receive 1000 samples. You don't have them yet, right, but be prepared. We're about to call your method add sample, and as we do so, we will be adding samples. Initially, there are no samples at all, so number of samples is 0. If we look down at the
The
method,
current number of sample is 0.
yes. If we look at the method add sample, every time it's called, we're adding at the index designated by current number of samples some element of information, and we're incrementing current number of samples.
That's right. So this way, and having this approach was also, it was a way for you to make sure that you were not receiving too many samples, and if so, well, for one thing, don't add more samples than you have room for, because it would crash, and you can inform that there would be a nice way to debug your code, to check this kind of thing.
Here it's important to realize that these two arrays that we have are somehow synchronized.
Yes.
In the sense that the element that is found at a certain position of samples has a correspondence with the element found at the same position within the other array.
That's right.
This is achieved by the method add sample because it's simultaneously adding information in the two arrays.
Right. Okay, so with that, you should be able to create your linear regression object and add all your samples. Now, the hypothesis function, well, it's pretty simple in this case. I mean, the definition says it's θ0 plus θ1 times x. So that's really all there is to this implementation. If we look at the cost, so the cost was also defined somewhere here. Here it is, and so you have to look through all the samples, and for each sample compute the difference between the current value as per the hypothesis and the value as per what you were told in add sample. And you do the difference, you square it, you go over all the samples for that, and then you divide by the number of samples. So this is exactly what this does. It starts at 0, go through all the samples. For each sample, look at the current value of the hypothesis, remove what you were told the value should be in sample values, and then square that and accumulate this answer over all the sample in a variable called response. And then you return response divided by the number of samples. Okay? And then the so-called B thing, the gradient descent, which is actually pretty short in the end. So we are going to iterate over a number of steps, and so the gradient descent itself is just that. Each step you do one descent. If we go back to the definition here, so you see the formula is, well, it's rather simple. θ0 is updated this way, θ1 is updated this way. Now, both of these things require a sum. So you need to compute the sum in order to be able to update θ0, and you need to compute the sum in order to update θ1. You can see that in the sum, you use the hypothesis function h. And so that's why I was insisting on the fact that these guys have to be updated simultaneously. If you were to compute the new value of θ here, and then update θ, and then try to compute the new value of θ1, well, every time you would use this hypothesis function at this point, you would have the new value of θ and the old value of θ0 and the old value of θ1. So basically, you would have a wrong hypothesis function. So you really needed to be able to compute these sums before you were updating θ0 and θ1. So, and if you just follow really strictly what it says here, well, you can see that, so the first thing is to sum over all samples, and over all samples, you apply the formula here. So the current hypothesis for the sample minus what you were told this sample should be worth, and this value is summed simply for alpha 0, for θ0, sorry, and for θ1 it is multiplied by the value of the sample. So I have two sums here, and initially there was 0, and as we iterate through all the samples, I just accumulate the value in sum 1 and sum 2.
Yep.
And at the end of this for loop, well, I am ready to update both theta 0 and theta 1, and I do that again by really strictly following the formula. So I take the current value of theta 0, I remove from that value 2 times alpha times this sum that I've computed divided by the number of samples, and that's it.
Yep.
Okay, so, and then we would generalize that to, well, so far we were looking at samples that had just one value.
One feature, yeah.
One feature. And now we are interested in trying to do the same thing with multiple features per sample, but always the same number of features per sample. So before you had m samples and their values. Now you still have m samples, but each sample has a certain number of features. So really you need to have an array of arrays.
Correct.
And so that was really the big difference. But we were also suggesting, well, we are asking to do something else. You see here, we were making a difference between theta 0 and theta 1, and it was really because of the formula. You ended up with two different values here. But there is a simple trick that says that, well, if instead of theta 0, you call that theta 0 times x0, for x0 is equal to 1, so that's the same thing. Say theta 0 times 1. Then, well, actually, you can just use the same formula for all the thetas. And that's what this was saying. You can use this formula here, which is now the same for every possible theta, as long as you add another feature, a dummy feature, if you want, x0, which is worth 1 for all the samples. So you had to do that in order to be able to use this simplified formula here.
So where before there were 2 cases, now there are n+1 cases in this interior part here.
Right. So
maybe we could look first at the data aspect of this,
yes,
class.
I have to change the file here. So sample matrix. So it used to be a sample array. Now it's an array of arrays, as we said. So when you create your linear regression now, you still have the number of samples, but now you want to pass the number of features, how many values you are going to have per sample. And we said that, so the number of features is going to be whatever you are taught, but you are going to store one more feature than what you were advertised here. So the matrix of samples, you have number of samples, but each entry in that first part of the array is going to be an array of number of features plus 1 to accommodate for this x0. And same thing for thetas. Thetas now, as you know, you have, well, you always add one more theta than you have features, and so it's now because it's a variable, you have to stick it in an array, and you create an array of number of features plus 1. And we are going to have to store temporary variables here for thetas, as for the same reason as before. And so we have a new variable temp theta, which is just also an array. All right. So shall we just skip over that? This is explained in the examples. You want to say something here?
No, I think the examples are showing precisely where the problems were with this add sample method. So we can skip over.
Oh yes, but this was the part you wanted to talk about. Yes, that's, we have, because we have created a samples matrix of number of samples times number of features plus 1. It was because the first entry, which is the entry 0 in an array, the first entry should have the value 1. So every time you add a new sample, the value 0 of that array here of current number of sample is going to have 1, and the other values starting at 1 now are going to be the one that is passed as a parameter. All right, and now, so and so if we go straight to gradient descent, you can see that it is even simpler almost, because now we have just one formula to follow, and really, if we follow strictly this, it becomes simple. This thing says, so every time you have an iteration, which you have here number of step time, so this is one iteration. Every time you have one iteration, what you should do is compute this sum here and update theta for all thetas. So it is iterating over every possible feature, and for every feature you go over every possible sample. And you also have the same problem as before, which is where you don't want to update theta as you are computing these sums, yeah, because otherwise you will end up again with thetas that have been partially updated. Some would have been updated and some would have not. So really you need to compute the sum, then you need to compute what is going to be the new value of theta, but hold on updating the actual theta, so that's why we have temp theta. Let's put this value in a temporary variable until we are done computing all the new values, and then we can update the data all at once. So we can see that on this thing here, where so we go over all the features. For each features, we are going to go over all the samples. We sum exactly what the formula is saying. Once we are done with that, we are almost ready to update theta, but we know we should not do that until we are done with the other computation. So we are going to put that in a temporary variable.
So you can see those as being the future theta.
That's right. That's theta at the end of that iteration. So you put it into this value here, and then, well, you are done all your feature and for all your samples, and then, well, you just have to go through all of your values for thetas and update them with so-called future data theta.
Yeah, so the future theta becomes the current theta.
That's right. So that's really all there is.
And what's elegant with that is that this piece of code actually works for the question that we were asking you to solve for question 1.
That's right. That's right. It's really a generalization of question 1.
Where in question 1 there were 2 cases. Here there's this single entry here. In the case of theta 0, the x here has value 1.
That's right. So you multiply by 1, that's the same thing.
Okay.
All right.
So I think that's all we wanted to say about this.
Yes, I think that's all for the assignment 1. So what we're going to do is we're going to post the code on GitHub.
Yes.
And put that link on.
Assignments will be marked, so there will be feedback there as well.
That's right.
If you don't understand the comments of your TA, just ask questions.
Exactly.
Okay, so how about this assignment 2?
Let's look at the assignment 2 now.
Okay, so assignment 2. Okay, so it's about a game that's well known.
Yes.
Called Minesweeper.
Actually, I was surprised to see it was still well known. I thought it was really something from way back then, but apparently
it used to be bundled with Windows, I believe.
Yeah. Yes. When I was a kid, that was the game.
Okay, so for those like me who've never used Windows, so there's a board. It's made of tiles. All the tiles are initially gray. Behind some of these tiles there are mines.
Yes.
The goal is to click on these tiles and some information will be revealed.
That's right.
If you're very, very unlucky, the first time you click on a tile, it's a mine, boom, you get this pop-up window. It says, ouch, you've lost the game, basically. The other cases are that if you're clicking on a tile and this particular tile didn't have a mine, it will tell you how many adjacent tiles contain a mine.
That's right. So you have each tile has 8 adjacent tiles, and so it can have anywhere between 0 and 8 mines in its neighborhood.
If
And
you're
the
even
number says how many there are, except if it's 0.
if you're very lucky, you've clicked on a cell where none of the adjacent tiles were containing a mine, so it's 0. Here we're representing this with a gray tile. Then if you've clicked that tile, there will be a process where you will be visiting the adjacent cells. If those cells are, again, storing the information 0, saying there's no tile adjacent, you will repeat this process and it will flood the entire region until you hit this boundary where you have numbers.
That's right. So automatically, all this part of the board is going to be cleared for you at once in one click. Maybe we can show as we talk about it. We can show the game. So we have here a version that should starting on the wrong screen. Let me just grab it here. Here you see it. So as Marcel said, well, initially you have to be lucky, and I was not. All right.
Okay.
So, well,
let's play again.
We can play again. That's good. So you can see, by the way, that this is the game. So once you have lost or won, all the tiles are revealed. Yeah. And if you have clicked on a mine, then that mine, the one from which you lost, is displayed in red, while the other ones are just displayed normally. So let's try again. My luck here again. Oh, much better. So this, you see, I clicked just once and all that cleared up. Yeah. So now I have information. I know that there is only one mine next to that tile, one next to that tile, 2, 1, 2, etc., etc. So then I can try to clear up some more stuff here. I don't have a lot of options here, but I can clear that up. I know, and that sort of helps. And then I am a little bit stuck here. No, I'm not. Yes, I am. Anyway, so I can try something else and see if I can clear up a new thing. That works. And I can keep like that, clearing more and more of all of that. And do that, well, until I either clear the entire region, I mean the entire board. That is, every tile that does not have a mine has been cleared. And if that happens, then I will have, so it takes a little while, so I'm just going to show here. You will have something like that that pops up. You have won. Okay?
Yep.
So that's the game.
So maybe we can just backtrack a little bit and give this little hint about how to successfully implement this game. So we're going to show you later that there's a very clean implementation for this game, very elegant implementation for this game that will allow you to focus on the different sub-problems independently. If you would like to implement the implementation without having too many headaches, this process where a very large zone of the board is cleared by the flooding process, you don't need to implement it right away.
That's right, because we are going to ask you to implement it using a stack.
Yes.
And so this is something that we are going to see here. We haven't started. And if you want to start working on that right away, well, I mean, we explained that in the document, but you can really postpone that part either because you are not familiar with stacks yet, or just because it's simpler to have a first version of the game that does not implement this flooding part, this flooding logic. the game is still playable completely without this logic. The difference is going to be that right now, if I, I clicked on this area here, and everything was cleared for me in one step. And if I had not this flooding implemented, then I would have to manually click on all this tile myself. But okay, that's a bit painful, but that would work.
Yeah, and really that's how I would implement the game. I would really, as a first step, make sure that my implementation of the game is correct. And then I would start to add these more complicated features, such as the flooding. So what it means, to be clear, is that you see when you're clicking on a tile and it contains a number greater than 0, you're simply revealing the tile. Well, what we're suggesting here is that if you're clicking on a tile that has a 0, do the very same thing. Just show the tile that has the blank surface and let the user click around to reveal all the adjacent blank tiles.
Right.
All right.
And so we are not suggesting that you do that for your assignments, but that as you are trying to get through your assignment, you first do it this way, and you can finish it this way, and then you can go back to that part of the assignment and finish it.
Yeah. So just maybe a 1 or 2 sentences on an idea here of the assignment, just to finish this part off. Really, this game was meant to be something where you will have to work with a stack.
Mm-hmm.
And in many implementation of the Minesweeper, what you will find is that people will implement the flooding using recursion. So we'll simply visit all the adjacent tiles. If they're blank, we will revisit the neighborhood of that tile, and again apply the same process for all the cells in the neighborhood. Every computer scientist knows that any recursive algorithm can be transformed into an iterative one where we're making the stack explicit. So that's what we're doing here. You will see that the actual algorithm is very simple and the solution is already given as pseudocode.
That's right.
All right, so shall we move to the MVC?
That's right. So the other reason why we are doing this video is to talk a little bit about the model view controller design pattern.
Yeah, so design pattern is something that is popular with some crowds. It's a very simple idea, when people encounter some problems, they find that they're always reusing the same kind of solution, and that solution that they've developed, they're giving it a name.
That's right.
In this particular framework that we're looking at, the design pattern is called Model View Controller. It's one of the most well-known way of building applications, has a lot of good features. The Java language itself was designed in a way to make it easier, make it easy to work with this design pattern, and we're going to use it for the assignment.
Right. So here, you are going to recognize things we have been talking about in class, which is trying to separate concerns as much as possible. So if you think about an application, there are a number of things that an application does, and it has to do all of them. If your application has a user interface, then it has to display something to the user. It has to know the state of the application. So for the game, it has to know, where the mines are hidden. It has to know how many times the user has clicked. It has to know all kinds of information about the game itself, and then it has to also understand the logic of the game. Mm-hmm. And so what I have described here are 3 somewhat separated problems that can be solved rather independently by separating them into three different concerns. So that's what model view controller is really. The view is the part that is going to display the state of the game. It's going to give an interface for it. The model is used to store the states of the game.
It's the data of this application.
Everything that relates to where we are at. This is in the model. The model doesn't know how it's being displayed. It doesn't know what you do. It doesn't understand the logic of the game, but it holds down the fort. It has the data. And then the controller is the brain. So the view shows to the user or somewhere what the model is like right now. And when something happens, like the user clicks somewhere, the view doesn't know what to do with it. It doesn't know. It's only capable of showing the model. So if something is happening on the view, then it will just delegate that to the controller. The controller is the brain. It doesn't really know how the view was displaying this thing at this very moment. All it knows is, well, this is what happened. It can tap on the model to know what is the current state, do some calculation, decide what to do with the current state of the application. Maybe some more time must be uncovered in this case. Several things should be done, and then the model states change. And once it's once the state is updated, the controller can go back to the view or to the views, we'll see, and tell the view or the views to update themselves because they are not reflecting the current state of the model anymore. The model was just updated, so they are going to ask the model for its new state, and it will display, update basically the UI.
So in the various examples that we're going to show you, the model will be somewhat simple.
That's right.
And you may not see the value of structuring the application this way because the application is so simple. But you can think that an application like UO Campus that you're all using has a very sophisticated model that stores your student information data. It's certainly a humongous piece of code. And we're strapping on the top of this model various views, some intelligence to allow you to interact with the data. So we're presenting you something simple. It's a good idea to understand very well how this simple application works, and then you can transfer over your knowledge to the Minesweeper and to something more complicated as well.
That's right. So if we look at this very example that you have here, so it's using the counter that we discussed earlier in the semester. So it is indeed a simple model.
Yeah, so maybe we can show just this one piece of code. The counter is really what we looked at in class. It stores a value, has a method increment, has a method get value, has a method reset. This example was presented in class, and when we presented it, we didn't talk about a graphical user interface. Here we're not changing the class counter at all. It does not know about the fact that it's going to be embedded into a graphical user interface.
Yeah, so I think that illustrates well, the separation here. You were able to create what amounts to the model now without absolutely knowing about a possible UI later or any kind of controller or anything like that. And that's the idea. Today I'm working on the model. Tomorrow I'm working on the view, and the day after I'm working on the controller. And you are going to see that as you are building the view, you are going to have all kinds of problems. You don't want at that time to worry about the logic of the game or how to store the data or all of that. This is yesterday's problem or tomorrow's problem. Today's problem, make the view work. So by splitting your work this way, you're going to end up having a much easier time completing your application, your assignment, and your application in general.
Yeah, in a real world setup as well, these different parts could be implemented by different teams.
That's right.
With different skill sets. The ones that will be implementing the model maybe need to have skill sets that include database and things like that, whereas the guys that will be developing the view and the controller will have different skill sets.
That's right. Yeah.
Okay.
So
shall we, maybe just a one line to add that not only this way of structuring an application makes it easier for you to debug, to construct, to develop the code, but it also allows for a lot of flexibility where we can actually have more than one view. These views could be for different purposes, so we could be adding a view for debugging purpose. We could be adding a view because the user has a particular problem. It could be that the person needs a voiceover or something like that. So we can attach these views. And what's great is that the model is so flexible, or the pattern is so flexible, that we can attach these views even at runtime during the application. So you can imagine that you're playing with your game, you suddenly discover that there's a problem, you say go to debug mode, and then in the console, many more elements of information would be displayed during the game.
That's right. And this kind of pattern here will not only let you do that, but it will be really seamless. If you want to create a new view, you just have to create your new view, tapping into your model, and then you have to inform the controller that there is a new view now, and the controller will update that new view along with all the existing views every time there is something that happens through that new view or through any other view, and all that will work sort of together very efficiently, and it's a very nice result, and something that you would find that you would have a lot of difficulties achieving if you were not following such a pattern. If you really had one big application where you would have your state and then your logic and then the way you present that, and then someone comes along and tells you, oh, can you also present it this other way? So now you try to find it, to find a way to do that, and it would be hell, really, very quickly. But this way, no, it's going to work as smoothly as it can possibly.
Yeah. So maybe you can show rapidly how this would work. So we've seen in class that on the view we can have some buttons, typically JButton objects. And we can imagine that on the view, the user has clicked on the increment button. When the button was clicked, that generated a call to action perform. In this case, we made sure that the listener for the button was the controller. So the method action perform of the controller was called. It knows that it's increment, that is the action that's needed. It will call the method increment of the model. The model increments its state, so the value becomes value plus 1. We're done with increment. The controller now informs the view, I'm done, update. The view will consult the model and say, what should be the value that I should be displaying on the screen? The value gets back, the view is refreshed.
Exactly. And so you will get something. So we will post this information. You're going to have access to that, and you are really strongly encouraged to try to understand that and to code it. But you will end up with something like that.
Yes. Yeah, I really think that before jumping into implementing the Minesweeper, you should at least understand the application where the model is as simple as the counter. And really we paid attention to make sure that the Minesweeper really has the same structure as the counter or other applications that we're developing in the course using this MVC model. So it's the structure is the same.
Exactly. All right.
All right. So good luck with this assignment. As always, use Piazza for your questions.
Yes, we're waiting for you right there. And as I hope you have seen, we are usually quite fast, and you get an answer quickly if you ask the right question there. And so use it, abuse it, and we'll be there.
All right. Bye now.
Thank you. Bye.